In this talk, I will keep defying the organizers because I won't talk explicitly about non-holonomic constraints, though we are a little bit closer because I will talk about virtual constraints. The main difference between actual constraints, physical constraints, and virtual constraints is in the fact that this time the nature of the constraints is not imposed by physics, but is imposed by man. So virtual constraints are always associated with a control system, so a dynamical system that we can actually control. And there are a set of constraints that we wish to impose on the system. For instance, we will see today that I wish that my system leaves some subspace invariant under the dynamics. So in that case, we'll say that those constraints are not physical constraints, but they are actual virtual constraints. So the main idea is that virtual constraints are always associated to a control system. And why should one wish to impose constraints? Well, the motivation for this problem comes from robotics, where, well, actually this term virtual constraints appeared there around 40 years ago because, for instance, in the walking problem, engineers see, well, the walking motion as a constraint they wish to impose on the dynamical system. And so the term was initially coined there. I will show in a minute in precisely which book. But in any case, these are some robots where virtual constraints were used. There are actually many cool videos about this Boston Dynamics Atlas robot. The first time virtual constraints appeared was actually more than 100 years ago by Appel, but not in the context of robotics or control system. 40 years ago, Grizzle and his lab started to use virtual constraints in the scope of walking robots, and this is kind of the motivation that, well, behind this notion of virtual constraints. One more remark about the difference, well, actually two remarks about difference between physical constraints and virtual constraints. Of course, in the left image, you have a system in which this box is constrained to move in a cylinder. This is an example of traditional physical holonomic constraints, a constraint on positions. The middle figure, we have a totally unconstrained system. And on the third figure, we have what would be a constraint imposed by control. So through the use of joints, we are imposing that this system cannot move, is forced to move in a vertical direction. So it cannot move outside that cylinder. So in practice, we are imposing constraint that traditionally comes from physical constraints, just that we are using controls. Another situation where virtual constraints appears is information control. We wish that some vehicles move, for instance, the green and yellow vehicles wish in the same direction and speed as the red vehicle. That would be also a virtual constraint, and that we would enforce by a control law. And finally, I wanted just to show you the difference between the equations that appear in regular holonomic constraints and virtual constraints. So suppose we have a variable length pendulum, which is a two-dimensional system. Of course, this system, well, is able to move around some fixed point, and also is able to stretch because the pendulum's rod has variable length. So if you by some physical reason, the length of the pendulum was a function of the angle, then we would be in the situation where you would have holonomic constraints. You'd apply, any method that you want to find the holonomically constrained equations, and you would obtain this set of equations. While in control equations, you will still have a system in principle evolving in 2 dimensions, and you have a control force. And that control force that you can use to enforce the desired constraint. So basically the main problems that we wish to address when we deal with virtual constraints, first of all, is the existence of a control law that leaves the constraints invariant, because maybe you cannot, your objective is not even possible. Maybe your desired constraint is not even possible to be realized through control law. So that is, of course, the first question. Then, and it is actually the first one is the only one that we'll address today. And the second one is when the controlled motion coincides with the physical constrained motion. And the third one is about the stability, considering that you don't start in your manifold of constraints that you wish to satisfy. Does your system converge into that manifold? So this is also a question that we are dealing with. These are some of the papers that we have produced, and the GSI paper is actually about the second one. So so let me start with just a simple recalling with what are physical non-holonomic constraints. These are constraints over the velocities that your system may assume. So these are typical examples of non-holonomic systems. Vertical rolling disk, it's like a rolling penny that is constrained to move in the direction of the orientation of the coin. The coin cannot move sideways. Then you have the snake board, and the last one, the Chaplygin sleigh, which is the prototypical example of non-holonomic system. We'll consider basically mechanical systems described by a Lagrangian function of mechanical type of kinetic energy coming from a Riemannian metric G minus a potential function V. And the typical, the Euler-Lagrange equations of motion for this Lagrangian are, can be written in Riemannian form using the Levi-Civita connection as the equation here below. So this is just the Riemannian form of Euler-Lagrange equations. On the other side, affine constraints, those we will address today, are of this form. So if you consider a one-form mu on the configuration manifold, the set of velocities satisfying these equations are what we call affine constraints. If that function b is 0, then we would have linear constraints. So we are including linear constraints in this model. So at each base point Q, at each point of the configuration manifold, these equations define a subspace of the tangent space. A subset of the tangent space. It's not a subspace because it's an hyperplane that may not contain the zero vector, but it is modeled on a subspace, of course. That's just a definition of an affine subspace. So a typical example of a non-holonomic system with an affine constraint is a ball rotating on a table, and the table is also rotating on its own. So this is, if the table does not rotate, then you'd get linear constraints. If the table do rotate, you get affine constraints. So, but as I told you, I want to discuss virtual constraints. So this is a notion associated with a control system. So my control system will basically be modeled on a mechanical system as the one I showed you 2 slides ago. but we'll add to this system linear controls. So something of this form. And the main question is, if I'm given a set of constraints, affine constraints that I wish my system to satisfy, can I find a control law that makes that affine distribution control invariant under the dynamics? So that is the main question for today. Just some terminology. These vector fields appearing here in the Riemannian form of all your Euler equations are vector fields which are called force vector fields, and then the span of these vector fields is called the input distribution. So based on this, the correct mathematical definition of virtual affine nonholonomic constraint is a mechanical control system for which an affine distribution A is controlled invariant. That is, controlled invariant means that there exists a control law for which the control loop system, the closed loop system, makes that affine distribution invariant under the motion. So if you if you start your motion, if you pick initial conditions inside that affine constraint, then your trajectories won't leave that constraint. So that's basically the meaning of being invariant, controlled invariant. Okay, so now what's left to establish if that such control law exists, and the condition for the existence, and actually for existence and uniqueness of that control law, is that the affine distribution A and our input distribution are transversal. Under this condition, we'll get not only the existence of the control law, but also its uniqueness. Let me just recall transversality in this context. Transversality in this context basically means that the two, at each point, the two subspace generate the entire tangent space, and the dimensions add up to the dimension of the tangent space at each point. Yeah, so basically an example where we have detected the existence of a control law is the example of a boat in the sea under the influence of a sea current, denoted here by C, by the function C. And in this context, we impose on our boat some controls, actually just one associated with this force field. So we can only exert control in the direction of this force vector field. Under these conditions, well, we wish to see if this affine constraint appearing here is control invariant. And this constraint basically means that the only way the boat can move sideways is due to the effect of the current. So basically that's the only thing. We are not forcing the boat to move sideways. And yeah, actually it turns out that in this situation, well, the hypotheses of our theorem are met, and there exists a control law, and in fact it's very easily to compute it. And the constraints are satisfied by our system. So this transversality condition was also proved by counterexample to be essential. We found, well, examples have actually not generally affine examples. In the linear case, in the case where our affine distribution is actually a linear distribution, we have found examples where the transversality condition is not met. In the first example, the input distribution is contained inside the linear distribution. In that case, the control law does not exist, so virtual constraint is not actually a virtual constraint. And in the case that the two distributions that generate the entire tangent bundle, but their intersection is not zero, I will call that in these counterexamples the distribution was linear. Then there existed multiple controls making the distribution invariant. I don't know how much time do I have. Am I 5 minutes? Okay. So, yeah. Now, meanwhile, we are trying to extend our results because I don't know if you noticed that we are working already in 3 different works about this topic, and our plan is basically to write the geometric theory about virtual constraints and eventually use it to understand the applications to robots, to robot walking motion. So the next step in this program would be to try to understand what is the geometric picture of nonlinear constraints. Nonlinear constraints are given by a constraint where the constraint function phi may be of any type. It has no condition on the velocities like being linear on the velocities or affine. So in this case, phi may be any smooth function. And in this case, the equations of motion, well, are given by Chetaev's principle. These are the corresponding to Euler-Lagrange equations for nonlinear in the presence of physical nonlinear constraints. These constraints, well, we have also written these constraints in Riemannian type. It's actually not important for what I have to tell you right now, but in any case, if you wanted to write Chetaev's equations in Riemannian form, this would be how you should do it. But in any case, the only thing here is that the terms, the vertical lift of this term appearing in the Riemannian form of Euler-Lagrange equations should be in some subspace that we call the S, the orthogonal to S. This S plays a role in the hypothesis that we must make in the following. So to guarantee the existence of a control law that will make our nonlinear constraints control invariant, we must make an hypothesis analogous to the one in the affine case, and in this case the hypothesis is that the tangent to the manifold of constraints is transversal to the input distribution. So this to the vertical lift of the input distribution. This is the analogous hypothesis. Is slightly more complicated. It's not exactly the same thing because it is not even on the same subspaces. This is in the tangent to the tangent bundle. These objects live in that double tangent bundle. But anyway, it's the analogous hypothesis, and we were even able to detect when a closed loop system for this unique control law exactly matches the trajectories of Chetaev's equation, so the physical non-holonomic constraint system. In any case, that is another question. Now then we have an example also for the nonlinear case, which is like a double pendulum actuated on the shoulder. So the shoulder here is the top joint, the one with angle Q sub 1, and we have some constraint that we desire our system to satisfy. And well, in this case we were able to, we were in the conditions in the hypothesis of our theorem, so a control law existed, and we've just checked that the constraint was satisfied, and basically this was a basic simulation. But the next step, which is even more important, is to address robot locomotion. As I said, this is the final objective of our program. The constraints appearing in robot locomotion are of nonlinear type, are very complicated, and definitely do not meet the assumptions in our existence theorem. So the two main difficulties with achieving our goal are actually work in a situation where maybe we do not have a unique control law, because in the conditions of our theorems we have a unique control. In this case, we can have a control, but it is definitely non-unique. And that is the first situation. Then stability problems. Maybe our robot initially does not satisfy the desired constraint, but we must be able to guarantee that it will eventually fall on the desired constraint. And third, we must be able to include impacts as long while the robot walks. So these are the main difficulties we are addressing at this point, and that's basically it. Yeah, thank you.
Thank you. Thank you, Alexander, for your talk. Some questions or remarks? Please.
I have one simple question. Is your control static feedback control? Or
Yeah.
Okay.
Feedback controller. Yeah.
Okay. And another question would be: have you looked whether your control would, for instance, preserve the passivity of your system? Like, if
Preserve what? Sorry.
The passivity of your system. Like, for instance.
No, we haven't looked at it.
Okay.
Okay, but that's a good question, of course.
More questions or remarks? So if not, we thank again to the speaker.
Thank you.